Okay, hello and welcome to my channel. Today we're gonna talk about the finite square well, and mainly we're just gonna talk about the bound state, not the scattering state, because that would be a little bit too advanced for now. So with finite square well, let's start with the potential. So this time I would like my potential to look something like this instead. The center would be 0 and the width would be 2a. So it would go from minus a to a, and if you remember with the infinite square well, this would span to infinity, right? But in this case, instead of going to infinity, it would just go to some number. And even more, for it to be even easier, take this to be minus v naught, so it would be a well instead of like walls. And this is your x-axis right here. Your x-axis would be there instead of here. So this would be easier for you to sort of do it. All right, so this would be 0 outside of this. Okay, I should have write this after I wrote that one. All right, so this is your potential right here. Be 0 outside and minus v naught inside this region. And today we're talking about bound states. So your energy is here. It would be under 0. Oh, negative energy. That's exciting. That is weird. Okay, so write explicitly. So bound state is less than 0. So what would you do now? So first thing first, you would like to write down your time-independent Schrodinger equation, I believe, every time. So I would just write it quickly in this form right away instead of doing the little step-by-step derivation. And you can see here E minus V naught. So that's your energy. There we go. This is what we have right here. So take this part, square. Okay, I'm forgetting a lot of stuff. Alright, as K for now. Okay, maybe K would not be so good because you'll know later on. Take this as alpha. Yeah, alpha would work. We'll take this as alpha. And if you remember, in the infinite square well potential part, we said that it is 0 outside, and in the inside, it, I believe, like root 2 over a and a sine function, right? So that would be the same right here. So the inside part would be some sort of trig function, and the outside has to be a decay. And it is different from the infinite square well potential that is the outside instead of an infinite potential. It is either 0 or finite number, so it can only push down so much. Meaning, okay, I will draw another picture for you to imagine. So imagine this is your potential, right? And with infinite for for it to be easier for you to imagine, this part right here is going to get pushed down so much because these are infinity. It cannot escape this part, so it can only be 0 here and 0 here. But here, it also have a force, the potential energy, to push it down, but this is not infinity. So your wave function can sort of escape this hole right here. So it is something like a little bit of that. It is still like a normal wave function, would still decay normally, but there would be some part that escape outside of this region. Meaning in this region there would be something instead of this, whose outside doesn't have anything, because there is an infinite potential pushing it down, destroying it immediately. Here it is not infinite, so there's gonna be something that would escape. So here we can get that if our alpha is inside, and just write that, and alpha is outside. So when it is inside, it is a trig function. Always trig function. And outside would be a decay. A decay is an exponential function. Right, there we go. So with this, let's get started with the inside. No, let's not split it like that. Let's do even and odd. Right, let's start with the even solutions. Even, so your psi of x would be equal to your psi of minus x. And for you to get the even solution, let's start with inside the region. Your x is inside the region. We can just start by putting it in your time independent Schrodinger equation, and I think this is not it, and it would be E minus V, but there's a minus here, so that would be minus V. And I believe some people would write this as V naught plus, right? It is, no, it is V naught minus the absolute value of E. So there are two ways to write this. It can be V naught minus the absolute value of E. And here, when you have this, your K, okay, my gosh, your K, which is either this or this, would be greater than 0. So let's take K equal to would be greater than 0. So it is a -1 because there's the minus there. We're gonna rewrite this minus K squared. Sorry, that is K squared. And remember, as I said, inside is a trig function. And if you do the math like I did in the infinite square well, you would get something that is like this. Your psi of x is cosine. One way for you to remember this is that this is even, and in mathematics, even is often associated with cosine, and odd is often the sine, and that is exactly the case here. The odd would be sine. Okay, that is inside. Now we're talk about the outside where your b is 0. Okay, which next is outside. Just write outside. And your b is 0. So with this case, that would be, this would be the case, and this is k squared psi, and outside meaning exponential because it has to decay to satisfy the conditions. Oh, okay, so you have this. The decay is simply just a Gauss, no, not really a Gauss, just a standard decay. Yeah, just write it alpha e to, yeah. So remember when I say that I don't want to use k for the inside and outside part, the reason is that in quantum mechanics, well, people often associate the inside with k and the outside with kappa instead. So this guy is kappa x. And for the odd solution, as I said, this, your psi inside, would be a function of sine, and the outside would be the exact same thing. The maybe another coefficient, but exact same decay sort of function here. So you can probably do that on your own. It is not that hard. So I guess that's it for today. This is just part 1 for the finite square well. Next video we're gonna take a look at unit-free numbers, which is part 2 for finite square well. So I guess that's it for today. Goodbye.